Hello students, in today's video we are going to see the trends in chemical reactivity of group 15 elements. In the previous videos we have seen the general characteristics of group 15 elements. What are the group 15 elements? Nitrogen, phosphorus, arsenic, antimony and bismuth. So far we have seen the atomic and physical properties of these group 15 elements. In today's video we are going to see the trends in chemical reactivity of these elements. When we say chemical reactivity, we are going to see how these elements react with other elements. For example, with hydrogen or with oxygen or with other metals. So that's what we are going to see today, the trends in chemical reactivity of group 15 elements. First, let's start with reactivity of these elements towards hydrogen. All the members of this group form covalent hydrides of the formula EH3 with hydrogen. See, group 15 elements, let's represent them as E, react with hydrogen to give you EH3 called as hydrides, and they are covalent hydrides, which means electrons are shared between the element and the hydrogen. So these are the list of hydrides formed by group 15 elements: NH3, PH3, ASH3, SBH3 and BIH3. And the names are ammonia, phosphine, arsine, stibine and bismuthine. So now let's see some of the properties of these hydrides. I want to make one thing clear. When we are talking about chemical properties of group 15 elements, we have already seen the chemical properties of the elements of group 15, which means we have seen about nitrogen, phosphorus, arsenic, antimony, bismuth, how their melting points change, how their boiling points differ and everything for the elements. Now we are going to see the chemical properties of their compounds, which means here we are going to see about hydrides. So when they ask you the melting point of the elements, that is different from the melting points of hydrides. So the trend changes. When we are talking about the trend of the elements, that is different from the trend of the hydride. So you have to be very clear what is being asked, whether the chemical property of the elements or the compounds like hydrides or oxides. So now we are going to see the chemical properties of hydrides, which means NH3, PH3, ASH3, SBH3 and BIH3. As you look at these hydrides, when you take NH3, the element here is nitrogen. Nitrogen is bonded with hydrogen. Here phosphorus is bonded with hydrogen, arsenic with hydrogen, antimony with hydrogen, bismuth with hydrogen. So as you move here, the size of the element increases, which means the size of nitrogen is smaller than phosphorus size, which is smaller than arsenic, which is smaller than antimony, and then which is smaller than bismuth. So as you move from this hydride to this hydride, the elemental size decreases, because what is same? Hydrogen is same in all the compounds. What is differing? The atom is differing, because we are talking about the hydrides of group 15 elements. So as you move along this, the size of the element increases. So as the size of the element increases, the bond length increases, because the central atom size is increasing. So the bond length between the central atom and the hydrogen also increases. So remember, as the size of the central atom increases, bond length will also increase, which in turn decreases the strength. So as the bond length increases, the strength of the bond becomes weaker. So as the bond length increases, it is easier to break the bond. So remember this trend. As the element size increases, which means the central atom size increases, bond length increases. We are talking about the bond length between nitrogen and hydrogen. So that bond length increases, so bond strength decreases. So based on this, we can talk about the trends of other properties. When we say bond strength decreases, do you think it's easier to break the bond or difficult? obviously it will be easier to break the bond as the strength decreases. So you need to give less energy as the strength decreases. So in this order, bond dissociation enthalpy decreases. What is bond dissociation enthalpy? The amount of energy required to break the bond. And we already said as you move from ammonia to bismuthine, bond length increases, so bond strength decreases. So when bond strength decreases, obviously bond dissociation enthalpy decreases. So when they ask you to arrange these hydrides in the decreasing order of bond dissociation enthalpy, how will you write? Ammonia will have greater bond dissociation enthalpy than phosphine, and then comes arsine and stibine, and finally bismuthine. Second one, stability of hydrides. Just now I told you strength decreases, bond dissociation enthalpy decreases. So obviously what will decrease? Stability decreases. When you are able to break some bond easily, then we say it is not that stable. And we have already said as you move from ammonia to bismuthine, bond dissociation enthalpy decreases. So stability of these hydrides decrease in this order. Next comes reducing character. What is meant by reducing character? It is a tendency to liberate hydrogen. If they liberate hydrogen, they can reduce some other species. So that is called as reducing character. And we know as you move from ammonia to bismuthine, stability decreases. So what will happen? The ability to release hydrogen increases. As you move this side, as the strength decreases, the tendency to lose hydrogen or release hydrogen will increase. So that in turn increases the reducing character, because reducing character is nothing but the tendency to release hydrogen. So the tendency to release hydrogen increases, or you can say reducing character increases. So that makes bismuthine the strongest reducing agent. So among all this, which is the strongest reducing agent? BiH3. All the others can also act as reducing agent, but NH3 being the most stable cannot act as a good reducing agent. Next comes basicity, which means the basic nature. What are Lewis bases? Those species that can give electron pairs are called Lewis bases. All these hydrides are Lewis bases due to the presence of lone pair of electron. Since the lone pair of electron is present on the central atom, all these hydrides are Lewis bases. Just like reducing character, which is measured as the tendency to release hydrogen, basicity or basic nature is the tendency to give electrons. The basic nature of these hydrides decrease down the group. So as you move from ammonia to bismuthine, the basic nature decreases. So this is the order of basicity of these hydrides. Ammonia being more basic in nature than phosphine, and it goes on. So the reason why the basic nature decrease in this order. As you look at the central atom, nitrogen atom has the smallest size and has a very high electron density. Since nitrogen being small in size, all the electron density is just consolidated in a small space. So its electron releasing tendency or the basic nature is the maximum. We are talking about ammonia. As you move down the group, there is a gradual increase in the atomic size. So when the atomic size increases, there will be decrease in the electron density on the central atom, because the size is getting bigger and bigger. So the electron is being spread out. The electron density is being spread out, not like ammonia, it is consolidated on the central atom. So as the atomic size increases, there will be decrease in the electron density on the central atom. So what will happen? The electron releasing tendency or the basic strength of the hydrides decrease in this order. So you should know the order, which means whether it increases or decreases, one thing. Second thing, you should know the reason why it is decreasing in this order. So remember, basic strength decreases from ammonia to bismuthine. Now coming to boiling points, the boiling points of the hydrides are expected to increase down the group because there is an increase in the magnitude of van der Waals forces. I told you already when we talked about the chemical properties of group 15 elements. As the size of the atom increases, the magnitude of van der Waals forces increase, so which in turn increases the boiling point. So we know as you move down the group, what is increasing? Magnitude of van der Waals forces increase, so that should increase the boiling point. But the boiling point of ammonia is more than that of phosphine and also ASH3. See the order. Phosphine least boiling point, then comes ASH3 and then NH3, SbH3 and BiH3. So in this order boiling point is increasing. So the boiling point of ammonia is more than that of phosphine and arsine. It is because of the presence of intermolecular hydrogen bonding in ammonia. Because nitrogen being more electronegative gets a partial negative charge and hydrogen gets a partial positive charge. So they tend to form hydrogen bonding with other molecule of ammonia. We call that as intermolecular hydrogen bonding. Now you need more energy to break the intermolecular hydrogen bonding also. So that increases the boiling point of ammonia. So that is the reason why this order of boiling point is followed by hydrides of group 15. So we have seen the trends in all these properties. Can you just think of thermal stability of these hydrides? What will happen to the thermal stability of hydrides of group 15 elements? Before that, what is thermal stability? It is defined as the stability to resist breaking down under the heat stress. So when you heat, whether these hydrides will break down, if they do so, in what order? That can be said from bond dissociation enthalpy. As you move down the group, the bond dissociation enthalpy of the hydrides decreases. So what will happen to the thermal stability? It decreases as you move from ammonia to bismuthine, which means ammonia is thermally stable, whereas bismuthine is not thermally stable. So thermal stability decreases as you move down the group. All you have to understand here is one way or the other, everything is related. So you can start from element size. As the element size, which means the central atom size in the hydrides increase, bond length will increase, that will decrease the strength. So when the strength decreases, bond dissociation enthalpy decreases. So what will happen to the stability? That will also decrease. And reducing character. What is reducing character? Tendency to release hydrogen. As the stability decreases, the tendency to release hydrogen increases. Because when you say stability decreases, which means you can easily break it down. When you can easily break that bond, hydrogen will come out easily. So when hydrogen is coming out easily, we are saying it is having reducing character. So when hydrogen is coming out easily along the group, we say the reducing character increases. And what happens to basicity? It decreases. What is basicity? The tendency to give electrons. As the size of the central atom increases, the electron density decreases. So the tendency to give away electron decreases. So we say basicity decreases. And just in boiling point, we have an exception where ammonia is having a higher boiling point than expected. It is due to the intermolecular hydrogen bonding. What is intermolecular hydrogen bonding? Why ammonia is capable of forming that? Because nitrogen bonded to hydrogen in ammonia is more electronegative, so it gets a partial negative charge, whereas hydrogen gets a partial positive charge. So it is forming hydrogen bonding with the another molecule of ammonia, and it goes on. And what is the reason for the increase in boiling point of these hydrides? Because as the central atom increases, van der Waals forces of attraction increase, so that in turn increases the boiling point. Now coming to the structure of hydrides, I told you these hydrides are covalent hydrides, and the central atom of these hydrides are sp3 hybridized. We have studied in grade 11 sp3, sp2 and sp hybridization. In sp3 hybridization, the geometry of the molecule will be tetrahedral and the bond angle will be 109.28 degrees. When there is sp3 hybridization, how many orbitals will be there on the central atom? 4 hybrid orbitals, because sp3, s1 p3, 3 plus 1 4, so there will be 4 hybrid orbitals. So out of the 4 hybrid orbitals, see, this is the central atom. It can be nitrogen, phosphorus, arsenic, antimony or bismuth. So central atom having 4 hybrid orbitals. 3 of the hybrid orbitals has overlapped with 1 as orbital of hydrogen. So 3 hydrogen is bonded here with the central atom, and 1 hybrid orbital contains the lone pair of electrons. When there are no lone pair of electrons, when there are only bond pairs, then the geometry of the molecule will be a tetrahedral. But when there is a lone pair, we have studied about this repulsion. Lone pair bond pair repulsion will be greater than bond pair repulsion. So this repulsion will be more than these repulsion. So because of this repulsion, there is a change in the bond angle. Actually, the bond angle is expected to be 109.28 degree, but because of the presence of lone pair and due to the lone pair bond pair repulsion greater than the bond pair repulsion, the bond angle decreases. For ammonia, it is 107.98 degree. The bond angle, HNH bond angle. Same way, HPH bond angle is 93.6 degree. Here for arsenic, it is 91.8 degree. For stibine, 91.3 degree. Here HBIH bond angle is 90 degree. So the first question, why the bond angle of hydrides is less than the expected tetrahedral bond angle, 109.28 degree? And the answer is because of the presence of lone pair, and the lone pair bond pair repulsion being greater than the bond pair repulsion, the bond angle decreases than the expected. And the second question, why there is a decrease in the bond angle down the group? As you move this side, the bond angle keeps on decreasing. Why? That's the next question. Actually, the difference in the bond angles is based on the electronegativity and the size of the central atom. For example, nitrogen has the smallest size with maximum electronegativity. We know nitrogen is more electronegative than any other atom in group 15. And I told you already, the electron density is very high around nitrogen when we talked about basicity. So as the size of the central atom increases, the electron density decreases. So now coming back to nitrogen, it has high electron density around nitrogen, which also means there is strong repulsion in the electron pairs around it. Around nitrogen, we have bond pairs, and bond pairs are also electrons. And now on nitrogen also electron density is more. So obviously there will be repulsion. Because of that repulsion, the bond angle increases. So ammonia has the maximum bond angle, 107.8 degree. But as you move down the group, the atomic size increases and the electronegativity also decreases. So as a result, there is gradual decrease in the electron density. So that in turn decreases the force of repulsion among the shared pair of electrons on the central atom. So that results in the decreased bond angles in the same order. So you should understand two things. The bond angle of all these hydrides are less than the expected tetrahedral bond angle. And the second one, the bond angles of all these hydrides are decreasing in this order because of the decrease in electronegativity and increase in atomic size and the decrease in force of repulsion between the shared electron pair. So the bond angle here decreases, here it is becoming more. I hope you understood the reactivity towards hydrogen and the trends in their properties. So questions will be like, they will give you these hydrides and ask you to arrange this in the increasing order of stability or decreasing order of basicity or increasing order of bond angle. Unless and until you understand the concepts and know the reasons why there is a decrease or increase, you will not be able to arrange them in the proper order. So try to understand the concepts and try to relate one property with another property so that you could come up with the proper order of the asked property. So next one is reactivity towards oxygen. Reactivity of group 15 elements towards oxygen. When the group 15 elements react with hydrogen, they gave hydrides of the formula EH3. Same way, when the group 15 elements react with oxygen, they form two types of oxides of the formula E2O3 and E2O5. For example, if you take phosphorus, you have P2O3, P2O5. So group 15 elements, when they react with oxygen, they form two types of oxides, E2O3 and E2O5. Regarding oxides, you should know the acidic strength. So to understand and arrange these oxides in the order of their acidic strength, you should understand some basic properties. You know nonmetals, metalloids and metals. When nonmetals form oxides, that oxides will be acidic in nature. Oxides of metalloids will be amphoteric in nature. Oxides of metals will be basic in nature. Keep that in mind. When nonmetals react with oxygen to give oxides, that oxides will be acidic in nature. Oxides of metalloids will be amphoteric in nature, which means they show both acidic and basic character. And oxides of metals will be basic in nature. And the next point that you are supposed to remember is, greater the electronegativity of the element, more acidic is the oxide. So if this is the oxide, we are talking about the electronegativity of this element. So when the electronegativity of the element is more compared to the other element in the oxide, then more acidic is the oxide. And next point, among the oxides of the same element, higher the oxidation state of the element, more is its acidic strength. This point, we are going to compare oxides of different elements. For example, I am going to take N2O5, P2O5, AS2O5. Here, oxygen is same, but what is different? Element is different. So how to decide on the acidic nature? Greater the electronegativity of the element, more acidic will be the oxide. So we have to remember this point when we are comparing oxides of different elements. When we are comparing the oxides of same element, for example, N2O, NO, N2O5, these are oxides of same element, and how to decide on the acidic strength? Look at the oxidation state of the element. We have to calculate the oxidation state of the element. More the oxidation state of the element, more will be the acidic strength of the oxides. So keeping these points in mind, let's try to arrange these oxides in the order of increasing acidic strength. First, let's take acidic strength of oxides of nitrogen. What are the oxides of nitrogen that we know? N2O, NO, N2O3, N2O4, N2O5. So here I have arranged them in the increasing order of acidic strength. And how do we decide on that? We are just calculating the oxidation state of nitrogen. Higher the oxidation state of nitrogen, more will be the acid strength. So these two are actually neutral, which means they don't show any acid strength. They are not acidic in nature. So N2O and NO are neutral. Next, acidic strength of trioxides. I told you group 15 elements, when they react with oxygen, they form trioxides and pentoxides. Now we are going to compare the acidic strength of trioxides of group 15 elements. So we have N2O3, P2O3, which will be dimerized to give P4O6, AS4O6, SB4O6. So now the acidic strength of trioxides. I told you among the oxides of different elements, greater the electronegativity of the element, more will be the acidic strength. And you know the electronegativity decreases down the group when you move from nitrogen to bismuth. So acid strength of N2O3 is more than P4O6, and then comes AS4O6 and SB4O6. So in this order, acidic strength decreases, which means these two are acidic in nature. As you move this way, as the acid strength decreases, these two are amphoteric in nature, and finally Bi2O3 is completely basic in nature. So to put it in simple words, as you move from N2O3 to Bi2O3, acid strength decreases and basic strength increases for these oxides, trioxides. And finally, acidic strength of pentoxides. Just like how we arrange the acidic strength of trioxides, we can do with pentoxides also, following the same point. What is that? Greater the electronegativity of the element, more acidic is the oxide. So the same order is followed. N2O5 is having more acid strength than P4O10, and then comes AS4O10, and finally SB4O10. See, this is actually trioxide, P2O3, AS2O3, but they dimerize. They cannot exist as P2O3, so they dimerize and they form P4O6, AS4O6. So these are the acidic strength of oxides of group 15 elements. So we have seen reactivity of group 15 elements towards hydrogen, towards oxygen. Now we are going to see the reactivity towards halogens. Group 15 elements, when they react with halogens, what are halogens? Group 17 elements. Fluorine, chlorine, bromine, iodine. We can represent halogens as X. When group 15 elements react with halogens, they form two types of halides, EX3, EX5. Just like how they form two types of oxides, trioxides and pentoxides, here they form two types of halides, trihalides and pentahalides. When it comes to pentahalide, nitrogen does not form pentahalide. It is because of absence of d orbitals in the valence shell. What is the electronic configuration of nitrogen? 1s2, 2s2, 2p3. So we don't have d orbitals in the valence shell of nitrogen. So nitrogen cannot extend its covalency beyond 4. So nitrogen does not form pentahalide, and what is the reason again? Non-availability of d orbitals. So the nitrogen cannot form pentahalides. And the next one, bismuth. Pentahalide of bismuth does not exist because of strong inert pair effect. I told you already what is inert pair effect. The reluctance of the valence s electrons. When you take the valence electronic configuration of group 15 elements, you have NS2, NP3. The reluctance of the valence S electrons to be available for bonding as compared to the valence p electrons due to their greater penetration in the nucleus. So when you look at the valence electronic configuration of group 15 elements, you have NS2 and P3. As you move down the group, the two electrons in the s orbitals, because of their greater penetration in the nucleus, because the atomic charge, the nuclear charge increases, so the s orbitals will be more penetrated into the nucleus, so they will not be available for bonding. Only 3 electrons in the p orbital will be involved in bonding, and this effect is called as inert pair effect, where the s orbitals are not available for bonding. So bismuth cannot form pentahalides. Nitrogen cannot form pentahalides because of the non-availability of d orbitals, and bismuth cannot form pentahalides due to the inert pair effect, as s orbitals are not, electrons in s orbital is not available for bond formation. And the next point, Pi5. When you take phosphorus, it is capable of forming pentahalides. You have PCl5, you have PBr5, but you don't have Pi5. And the reason why Pi5 does not exist is that because of steric factors. Phosphorus cannot accommodate 5 atoms of iodine as they are bigger in size. When you look at the halogens, we have fluorine, chlorine, bromine, iodine. Iodine has the bigger size, and phosphorus cannot accommodate 5 atoms of iodine around it. So Pi5 does not exist. And the next point, pentahalides are more covalent than trihalides. When we say covalent, they share electrons. The atoms of group 15 elements share electrons with atoms of halogens. The reason why they cannot form ionic compounds is that if they want to form ionic compounds, group 15 elements should lose 5 electrons so that they can form E+5 ion. But you know, it is very difficult to lose 5 electrons to form E+5 ion. So they preferably share electrons. So that's the reason pentahalides of group 15 elements are more covalent than trihalides. Now coming to trihalides. All the trihalides like PCl3, ASI3 or BRF5, all these are, BRF3, all these are very stable in nature, except trihalides of nitrogen. When you take the trihalides of nitrogen like Ni3, NBr3, NCl3, all of these are unstable because of the large difference in the size of nitrogen and the halogen atom. Because you know nitrogen is of very small size, and look at the size of the halogen, chlorine, bromine, iodine. As the size is getting bigger and bigger, there will be large difference in the size of nitrogen and the halogen atom, and that is the reason the trihalides of nitrogen are unstable. But one trihalide of nitrogen, which is NF3, is stable because both nitrogen and fluorine are small in size, so the bond formed between them is strong enough. Just like pentahalides, all trihalides are predominantly covalent except BiF3. BiF3 is ionic in nature. Next one is reactivity of group 15 elements towards metals. All the group 15 elements react with metals to give binary compounds. And these group 15 elements exhibit +3 oxidation state in these binary compounds with metals. So, sorry, -3 oxidation state in these binary compounds. Now look at these example, Ca3N2. Here nitrogen exhibits -3 oxidation state with the metal calcium. So this is called as calcium nitride. Same way we have calcium phosphide, sodium arsenide, Na3AS2, zinc stibide, and magnesium bismuthide. In all the binary compounds with metals, group 15 elements exhibit -3 oxidation state. So we are done with the chemical trends of group 15 elements. We have seen the reactivity towards hydrogen, oxygen, halogens, and towards metals. Read the textbook part so that you will have a clear picture about all these concepts. Thank you.